Hey everybody, welcome to our lecture on limits. And I'll start with a definition, and we'll work with the definition over and over again in the sense that we will analyze what it really says, and then we'll do some examples. First of all, W is a complex valued function of Z, where Z is a function of X and Y. So given the complex valued function W equals W of Z, or W function of X and Y, the statement, the limit as Z approaches Z naught of W of Z equals L, where L can be a complex number, means that given epsilon, any epsilon greater than 0, there exists a real number delta, where delta is a function of epsilon. So given any real number epsilon greater than 0, there's a real number delta, a function of epsilon greater than 0, such that if Z minus Z naught is less than delta, then WZ minus L is less than epsilon. Now let's just analyze this and say what this is really saying. First of all, notice what this is. This is the distance between Z and the point Z naught. Notice what this is. This is the distance between the function W of Z and the complex number L. And we'll get back to that in just a second. What does this statement mean? The limit as Z approaches Z naught of W of Z equals L. It means that if we make Z sufficiently close to Z naught, that will force W to be as close to L as we want. Or looking at it from the other direction, we can make W of Z as close to L as we want just by making Z sufficiently close to Z naught. Yeah, I like that better. That's a much better way of saying it. This statement means the following. We can make W of Z as close to the limit L as we want just by making the variable Z is sufficiently close to Z naught. If W of Z isn't as close to L as we would like, no problem. We'll just make Z a little bit closer to Z naught. And if that still doesn't solve the problem, we'll make Z even closer to Z naught. And eventually that will force W of Z to be as close to L as we want. So, the limit of W of Z as Z approaches Z naught equals L means that we can make W of Z as close to L as we want. How close? Within epsilon units, no matter how small epsilon is. This is saying that we can make W of Z as close to L as we want within epsilon units of L, where epsilon can be a tiny, tiny real number. And we can do this provided that we make Z sufficiently close to Z naught. Well, how close does Z have to be to Z naught? Less than delta, where delta depends on epsilon. So in other words, how close do we have to make Z to Z naught in order to make this happen? It depends on how small epsilon is. If epsilon is a real small number, that means that WZ is really close to L, which means that Z better be really close to Z naught. In other words, if epsilon's a small number, delta is going to have to be a small number too. And if we make epsilon even smaller, then we're going to have to make delta even smaller. So this value of delta depends on epsilon. How close we make z to z naught depends on how close we want w of z to be to L. Now, instead of writing this in terms of the complex variable z, we can write it in terms of xy, where z is equal to x plus iy. The limit as xy approaches x naught y naught of w of xy equals L means that given epsilon greater than 0, there exists a delta which is a function of epsilon, such that if x and y, or rather, if the ordered pair xy and the ordered pair x naught y naught are sufficiently close to each other, then w of xy and the complex number L will be sufficiently close to each other. So if we want w of xy to be very close to our limit L, in other words, if epsilon is small, then x of xy better be very, very close to the ordered pair x of naught, y sub naught, which means that delta is going to have to be small. Now, let's look at an example. Okay, here's a good exercise to do. Prove that the limit as z approaches 0 of x cubed over x squared plus y squared equals 0. And in the context of what we've just been talking about, this is w of z, or w of xy. 0 is our limit, L. And this thing, that's the complex number z sub naught. So what this is saying is, we can make this function as close to our limit 0 as we want, just by making z sufficiently close to 0. So let's see how we go about doing that. So let me just tell myself in words exactly what it is that I need to do. If I write down in words what I need to do, then usually it's not too difficult to do it. And according to the definition of limit, we need to show that given epsilon greater than 0, there exists a delta greater than 0, such that z minus z naught less than delta implies that w of z minus the limit is less than epsilon. In plain speak, what we're trying to show is that we can get w and L as close as we want. We can get w as close to L as we want. How close? Less than epsilon units apart. So we can get w and our limit as close together as we want, less than epsilon units apart. And how do we do that? We do that by getting z sufficiently close to z naught. And how close does z have to be to z naught? Less than delta units. So if we have z and z naught within delta units of each other, then we can force w of z and the limit L to be within epsilon units of each other. And so here's how it works. We pick an epsilon out of the year, sort of like a challenge. We'll pick a small epsilon and say, we can make w of z within epsilon units of L. And the challenge, or the response to the challenge is, we have to find z close enough to z naught to force this to happen. So the first thing we do is, well, I'll tell you what. Yeah, I guess the first thing we do is we say epsilon greater than 0 be given. No matter how small epsilon is, this says that we can make our function within epsilon units of our limit 0. And so now we've got to find a delta so that if z is within delta units of z naught, then this function will be within epsilon units of our limit. So let epsilon greater than 0 be given. And let delta equal a function of epsilon greater than 0 be given by, and you know what? I have absolutely no idea what delta should be, but I'm going to pretend like I have the answer. And then I'm going to say, finally, let z minus 0 be less than delta. Now, I think right about this time, I need to go to some scratch work. I need to know what goes here. I don't know what goes here. So I'm going to do some scratch work. And the scratch work is something that we always have to do in a proof like this. But when we see the proof in a textbook, they conveniently omit the scratch work and just put the proper value of delta in here. But we're going to do the scratch work. So here's where I start my scratch work. And typically I apportion a part of the page separate from the exercise to do this scratch work. And I encapsulate my scratch work in a box and then go back to the exercise I'm working on and fill in the proper values. But in my scratch work, I write out what it is I'm trying to do. I say, given epsilon greater than 0, we need a delta function of epsilon greater than 0 such that z minus 0 less than delta implies our function minus 0 less than epsilon. In other words, z within delta units of 0 implies our function is within epsilon units of 0. That's what I'm trying to get. And I don't know what to do, so I'm going to play with this thing and see if anything nice happens. And, you know, this looks familiar. X squared plus y squared, that's the modulus of z. Z equals x plus iy. So x squared plus y squared is the modulus of z, but we're in the habit of calling the modulus of z r. So r squared equals x squared plus y squared. And since I have the denominator written in terms of r, maybe I should write the numerator in terms of r also. If it turns out not to be a good idea, I can always go back and change what I've done. So x is r cosine theta. So x cubed is r cosine theta cubed. And that's equal to r cubed cosine theta cubed and son of a gun, I can cancel r squared from top and bottom. So that gives me the modulus of r cosine cubed theta and we have this property that the modulus of a product is equal to the product of the moduli. So we can split this up. We're going to get modulus of r times modulus of cosine cubed theta. And by definition, r is a positive real number, so we don't need a modulus around it. We'll just write r modulus of cosine cubed theta. And cosine cubed theta is a real number, so this is an absolute value. And what do we know about the absolute value of cosine of any angle? The cosine of any real number is going to be less than 1. So this thing less than or equal to 1, and it's positive, or non-negative anyway. So I can write this is less than or equal to r. Well, that's kind of significant, I think. I'm not sure what it's significant of. But here's what I started with. And this thing turns out to be less than or equal to r. Now, what did I want to be true of this thing? I want this thing to be less than epsilon, right? And I know that this thing is less than or equal to r, so I can force this thing to be less than epsilon if I just stipulate that r is less than epsilon. So if I make r less than epsilon, this thing will be less than epsilon. Now, r less than epsilon, that's the same thing as epsilon greater than r. But what is r? That's the modulus of z, right? And let's tie this in with something else that we want. We want the modulus of z minus 0 less than delta. But wait a minute. Modulus of z and the modulus of z minus 0 are the same thing. So let's write z minus 0 here. So what we've just discovered is z minus 0 is less than epsilon. Epsilon greater than r equals modulus of z equals modulus of z minus 0. So epsilon is greater than modulus of z minus 0. Or z minus 0 modulus is less than epsilon. Now we want z minus 0 less than some delta. Well, we've got modulus of z minus 0 less than epsilon. So why not let delta equal epsilon? And this implies the modulus of z minus 0 will be less than epsilon, which equals delta. In other words, modulus of z minus 0 is less than delta. So we have our delta. Delta equals epsilon. That's what we didn't have before. And I say that usually when I do scratch work, I write it on a part of the page that's sort of separate from the rest of the exercise that I do. And I encapsulate it just so that I know that this is scratch work. Now I can go back to where I was when I got stuck because I didn't know what delta was. And I'm going to use the results of the scratch work to fill in the blank for my delta. So we're back to where we left off. That we have epsilon greater than 0 be given. And we have delta equals some function of epsilon greater than 0, given by delta equals epsilon. And we have z minus 0 or z minus z naught less than delta. So let's see where this goes. X cubed over x squared plus y squared minus 0, where 0 is the limit. And we can tidy this up a little bit. This is the modulus of x cubed over x squared plus y squared. And remember in the scratch work, we looked at x squared plus y squared, and we said, that looks familiar. That's r squared. Okay. So modulus of x cubed over r squared and we shrugged our shoulders and we said, well, if we're going to re-express the denominator in terms of r and perhaps theta, we might as well do the same thing for the numerator. X is X is r cosine of theta. So x cubed is r cosine of theta cubed over r squared. And this becomes r cubed cosine cubed theta all over r squared. And we realize we can cancel an r squared from numerator and denominator. And that leaves us with what? Just the modulus of r cosine of theta cubed. That we have the modulus, or in this case, really just the absolute value of a product. So we can break this up into the product of the absolute values. And r is always positive anyway, so we don't need absolute value sign around the r. Oh yeah, and I remember now in our scratch work we said absolute value of cosine is never greater than 1. So absolute value of cosine cubed is never greater than or equal to 1 either. This thing is less than or equal to 1, greater than or equal to 0. So I can write less than or equal to r. And r is the modulus of z, isn't it? And we said, you know what? Modulus of z, that's actually equal to z minus 0 in this case, where 0 is our z naught. And, you know, I'm taking a few steps for nothing. Every now and then it's a good idea to step back and look at what we've just done and also consider where we're trying to go with this. And you know what? No, I guess I'm okay. Z minus 0 modulus is less than delta, okay. But delta is equal to epsilon. So what exactly have we shown here? In this example, we've shown that z minus z naught less than delta implies, and let me write z naught back here since we're restating what we just did. Z minus z naught less than delta implies w of z minus our limit is less than epsilon. That's what we've shown. And I'm going to restate that just so that we know what we've just done. Z minus 0 less than delta, where delta is our z sub naught, implies this thing minus 0, z cubed over x squared plus y squared minus 0. And the significance of this is that this is w of z minus L is less than epsilon. That's what we showed. So z minus z naught less than delta implies wz minus L less than epsilon. That tells us that the limit of w of z as z approaches z naught is equal to L, the limit, 0, which I state up here. So here's my W of z, here's my limit, and here's z minus z naught. So I will encapsulate this to emphasize that this is what we have just shown. Now let's look at a more pathological case. I'd like to illustrate a point here. And the point is this. In order for the limit of W of z as z approaches z naught to exist, in other words, in order for the limit of W of z as z approaches z naught to equal some complex number L, the limit has to exist and be the same limit regardless of the path that z follows en route to z naught. So if z goes to z naught along one path and W of z goes to L, it also should be the case that that W approaches L as z approaches z naught along other paths. And yet, in general, that's not necessarily true. Given that the function W of z approaches L as z approaches z naught along one path, it does not necessarily hold true that W of z approaches L as z approaches z naught along a different path. Just because as z approaches z naught along one path leading to z naught, W approaches L, it's not necessarily true that W will approach L as z goes to z naught along other paths. And we'll look at an example that illustrates that. This example shows why it is that we have to be careful. So we compute the limit of this function as z approaches 0, or in terms of x and y, we consider the limit of this function as xy approaches the origin, 0, 0. And just for the sake of example, let's say that xy is approaching the origin along the positive y-axis. So here's the origin, and xy is a point on the positive y-axis, and xy is approaching the origin in that direction. Well, in this case, since xy is a point on the positive y-axis, then y is equal to 0, isn't it? So this point xy is really x0. If we're on the x-axis and we stay on the x-axis, y is 0. So this expression really is x times 0 on top, x squared times 0 squared on the bottom. I'm sorry, x squared plus 0 squared on the bottom. And that's just going to be equal to 0. So supposedly, from our computation, the limit of xy over x squared plus y squared is equal to 0. But let's have xy approach the origin along a different path. Let's suppose that xy approaches 0 along the line y equals x. Now, what is this going to look like? Here's the origin, and here's the line y equals x. And if xy is a point on this line, then we can say this. The limit is xy approaches the origin of xy over x squared y squared is the same as the limit is xy approaches the origin of, well, let's see. Any point on this line is such that the x and y coordinates are equal. So the y coordinate equals the x coordinate. And we can say that xy is the same thing as x times x. And we have x squared on the bottom. Since y equals x, we could write this as x squared. So this is the limit as xy approaches the origin of x squared over 2x squared. So that's the limit xy approaches the origin of 1/2. Well, the limit of a constant is just the constant itself. Well, here, as xy approached the origin along the positive x-axis, the prospective limit was 0. And now the prospective limit is 1/2 when xy approaches 0, 0 along the line y equals x. So let's recap what we just discovered. as xy approaches the origin along the positive y-axis, our function, what was that, xy over x squared plus y squared, approaches 0. But as xy approaches the origin along the line y equals x, our function xy over x squared plus y squared approaches 1/2. So in other words, the value that our function approaches as xy goes to the origin depends on the path that xy follows getting to the origin. If xy goes to the origin along this path, our function approaches 0. As xy approaches the origin along this path, our function approaches the value of 1/2. So that leads us to conclude that the limit as xy approaches the origin of our function f of x, or w of z rather, the limit of our function does not exist. Okay, first theorem. Let w equal u of xy plus I v of xy. Let it be defined in the immediate vicinity of the point x naught, y naught, except perhaps at the point x naught, y naught itself. Then the limit of this function as xy approaches x naught, y naught exists and is equal to u naught plus I v naught exactly when the limit of u of xy equals u naught and the limit of v of xy equals v naught. Now, the emphasis of this theorem is just that the limit of this function exists if we can compute the limits of the real and imaginary parts separately. If the limit of this function exists, then we can compute it by computing the limits of the real part and the imaginary part separately. And if we can compute this limit by computing the limits of the real parts and the imaginary parts separately, then the limit of this function exists. And it's the sum of the limit of the real part plus I times the limit of the imaginary part. So essentially, if the limit exists, and only if the limit exists, we can compute the limit of a complex valued function by computing the limit of the real part and computing the limit of the imaginary part. Now let's get some more theory. Okay, theorem number 2. And excuse me, I just saw a flaw in my note giving. Okay, that looks better. Suppose that f of z and g of z are complex valued functions, and that the limit of f of z is a, and the limit of g of g of z is b. Then the limit of a constant times f of z is just c times the limit a. So the limit of a constant times a function is just the constant times the limit of that function. You know, I must be in an X frame of mind here. Okay. The second theorem tells us that if we have the limit of the sum or difference of functions, that turns out to be the sum or difference of the limits of the functions. So if we're computing the limit of a sum or difference, we can do it term by term. We can compute the limit of the first term, and then go to the limit of the second term, and so on, and then just add them together afterwards. C, we have the limit of the product of two functions, and that's the product of their limits. So to compute the limit of a product, compute the limit of the first factor, compute the limit of the second factor, multiply them together. In part D, I'm going to have to add a disclaimer here. I just thought about it. The limit of a quotient of functions is the quotient of the limits. So in other words, we can compute the limit of the numerator and put it over the limit of the denominator. Now, guess what disclaimer I have to put here? Shame on me. This works just as long as b, the limit of g of z, is not 0. And that makes sense. If the limit of the denominator is 0, we're not going to put 0 down here. So those are some helpful limits on, some helpful theorems on limits. We also have some limits on continuous. We have some theorems on continuous functions. I'll put that up along with a definition of continuity. A little bit of info about continuity here. The function w equals f of z is continuous at the point z equals z naught, and I'm defining the term continuous at the point. W equals f of z is continuous at the point z equals z naught, exactly when the limit of f of z equals f evaluated at z naught. So, to put it a different way, the functions that are continuous at the point z equals z naught are exactly those functions whose limits as z approaches z naught can be computed just by plugging z naught in for z. If we can compute the limit by plugging in, that function's continuous at that point. Now, theorem. Suppose f of z, which is u of xy, real part, plus I v of xy, the imaginary part, is defined in the immediate vicinity of x naught, y naught. Then f of z is continuous at the point z naught equals x naught, y naught, exactly when u of xy and v of xy are continuous at the point. So a complex valued function is continuous at a point z naught exactly when the real part and the imaginary part are continuous at the point z naught. And now I'll just define the term continuous as opposed to continuous at a point. We define the word continuous as opposed to continuous at a point. A function w equals f of z is continuous exactly when it's continuous at every point in the set of complex numbers. And if we want, we can restrict this definition to a particular subset of the complex numbers. Let's say the set A is a subset of the complex numbers, and we can say that the function f of z is continuous on the set A exactly when it's continuous at every point in the set A. Some theorems about continuity. Sine of x, cosine of x, e to the x are continuous for all real numbers x. Natural log of x is continuous for all positive real numbers x. And I guess I'll call this one 0. Polynomials are continuous for all complex numbers z. The sum or difference of continuous complex valued functions is continuous. A constant times a continuous complex valued function is continuous. So you multiply a continuous function by a constant, you get a continuous function. You add or subtract continuous functions, you get a continuous function. The product of continuous complex valued functions is continuous. So you multiply two continuous functions together, you get a continuous function. The quotient of continuous complex valued functions is continuous. Disclaimer, at those z values that do not make the denominator 0. The quotient of continuous complex valued functions is not continuous for those values of z that cause division by 0. And finally, the composition of continuous complex valued functions is continuous. Now, these may help us from time to time. If we know these properties, it may save us from doing some laborious computations. Let's do some examples, okay? Okay. Here's what I see. I see the limit of the quotient of polynomials. And polynomials, okay, the quotient of polynomials is the quotient of continuous functions. So therefore, it is a continuous function. Let me run that by you again. We have the limit of the quotient of polynomials. But polynomials are continuous. So that means that we have the quotient of continuous functions. And that means that we can compute this limit just by plugging in the number that z approaches, provided that that number doesn't make the denominator 0. And it doesn't. So this function's continuous. We can compute the limit just by plugging in. Whoops. Oh, let's see, 1 plus I squared, this is something at an angle of pi over 4. If we square it, we're going to get purely imaginary, I think. So let's see, 1 squared plus 2 times the first times the second is 2I, plus the second squared, yep. So we get 2I plus 2 plus 2I plus 2 over 1 plus 2I. Let me just make sure I did that the way I wanted to do it. 2 plus 2I plus 2. And that's 4 plus 4I over 1 plus 2I. And to divide by a complex number, we multiply by its conjugate. So we're going to get 1 minus a negative 4. And up top we get 4. And we get 8i. No, just 8 rather. And we get 4i minus 8i is negative 4i. I hope. Four plus 8 is 12, minus 4i over 5. And is that what I think I should get? I don't think so. Well, then again, maybe it is. The result didn't seem familiar to me. Just as a remark, notice how we simplified everything. That we said this was the quotient of polynomials. So it was the quotient of continuous functions, therefore continuous at every value of z except values of z that cause division by 0. If we plug this in, does it cause division by 0? No. So this function is continuous at that point. So we can compute its limit just by plugging this value in. Here's a nice one. We're computing the limit of the quotient of polynomials. Polynomials are continuous, so this quotient is a continuous function, except for any z value that causes division by 0 here. So essentially, we can compute this limit by plugging in because it's continuous. So let's plug in. Plug in 2 plus I for z, so we'll get 2 plus I squared minus 2 times 2 plus I plus 1 minus 2i. And we plug in the bottom. 1 minus I times z, which is 2 plus I, minus 3 plus I. Okay. 2 plus I squared. Oh, crud. So we get we get the first squared, which is 4. We get the last squared, which is minus 1. And we get 2 times the first times the second, so that's 4i. 3 plus 4i. And then we get minus 4 minus 2i. And we get plus 1 minus 2i. And on the bottom, we get 2. I times negative I is 1. And we get minus 2i plus I. So that is 3, 4. Is that right? 4 minus 2I. Do I believe that? Plus 2 plus 1 minus 2I plus I. Okay, I messed it up once before, so I'll check it. This will be the third time. 2 plus 1 minus 2I plus I. Okay, so that's what it should be. 3 minus I and minus 3 plus I. That does not look good, but I think that's what it is. Zero on the bottom. On top, we have 3 minus 4 is negative 1 plus 1 is 0. 4I minus 2I is 2I. Minus 2I is 0. Okay. When we plug 2 plus I in for z, the top becomes 0. When we plug 2 plus I in for z, the bottom becomes 0. What that means is that z minus this number is a factor of top and bottom. And here I'm just using the fact that if we plug a number into a polynomial and we get 0, x minus that number is a factor, or in this case, z minus that number is a factor. So z minus 2 plus I is a factor of top and bottom. Which means essentially, since z is approaching 2 plus I, but it never gets there, we can compute this limit by canceling the common factor. So let's see, the numerator is z squared minus 2z plus 1 minus 2I. That's the numerator. And this is equal to, this is equal to what? Z minus 2 minus I times something. Since this has to be a factor of top and bottom, this has to be a factor of the numerator. So this times something else is going to give us the numerator. Now, what is that something else? Well, we got a z squared right here, which means I guess we need to have z here. So I'll put z here. And what else do I see? I don't know. I better crank some of this out. I have z here. Z times z is z squared, which is what I want. Z times negative 2 is negative 2z. Z times negative I is negative iz. This I want. This I want. This I don't want. I have negative 2z and nothing else. So somehow, what I put in here is going to have to annihilate that I times z, or this negative I times z. So I'll say, what the heck, let's try positive I. And I may have to add another constant here, we'll see. I times z is plus iz, which is exactly what I want. So those two add up to 0. And I times negative 2 is negative 2i. And I times negative I is plus 1. Now how are things looking? Z squared minus 2z. These cancel each other out, thank goodness. And this thing and this thing are actually the same. Okay. Well, I just figured out how the numerator factored. Z minus 2 minus I, Z plus I, so I can erase this. And I have how the top factors. Okay. Now, this thing is also a factor of the bottom. So I'll write denominator. And my denominator, wow, is this really my denominator? Okay. 1 minus I times z minus 3 plus I. And that equals this thing times something. I know this is a factor of the denominator. It looks kind of weird, but it is a factor of the denominator. So this times something else gives us the denominator. We'll see what. Now, what do we have for coefficients of z? We have 1. We have minus I. So I've got to have a 1 here and a minus I here. And this gives me 1z minus iz. Now, how does the rest play out? 1 times negative 2 is minus 2. 1 times negative I is minus I. Negative I times minus 2 is plus 2I. Minus I times minus I is I squared, which is negative 1. And let's see. This is minus, whoops, no it's not. This and this give us minus 3. And these two give us I. minus 3 plus, that's it exactly. Okay. This is the factorization of the denominator. So I will write that down. Z minus 2 minus I times 1 minus I and are we going to cancel? You bet your bottom we are. We got rid of the troublemaker, that factor in top and bottom that causes zero division. We'll plug in again. It's the quotient of polynomials. And this time the denominator is definitely not going to be 0. So this is a continuous function. We can compute the limit by plugging in. And so we're going to get for z 2 plus I over 1 minus I and that's going to equal 2 plus 2I over 1 minus I, and that's 2 plus 2I over 1 minus I times 1 plus I, 1 plus I, and that gives us 2 on the bottom, and on top we get 2 plus 2I minus 2 let's see, I times I is negative 1, so this is minus 2. Plus 2I. I times 2 is plus 2I again. I times 2I is negative 2. Now let me just make sure I did that again correctly. 2 minus 2, 0. 2I plus 2, yeah, okay. So, after having done all of that mess, we'll encapsulate our results. And I think I got one more quick exercise. Okay. One concluding example. State y, the limit as z approaches z naught of cosine of x, natural log of y squared plus 1 plus I e to the x is equal to cosine of x naught plus y naught, natural log of y naught squared plus 1 plus I e to the x naught. And how do I reason on this? We can compute the limit of this thing, and the limit exists if and only if the real part, the limit of the real part, and the limit of the imaginary part both exist, in which case the limit of this entire expression is the limit of the real part plus the limit of the imaginary part. And these limits exist because these are continuous functions, which means we can compute their limits just by plugging in the values that x and y are approaching. So each of these is a continuous function. We can compute their value by plugging in what x and y are approaching. And so the limit of the real part exists, the limit of the imaginary part exists, so the limit of the entire expression exists and is the sum of the limit of the real part plus the limit of the imaginary part.